All right, so now we have to write what T1 is, right? So that kinetic energy, you can just look at it for the system, for those two different things, right? So this will be just equal to, you can write it as, let's say, half ma VA squared plus half mb VB squared, right? So writing out this energy conservation expression, you get 0 plus 0 is equal to 1 half ma VA squared plus 1 half mb VB squared, right? Minus mbg d sine, whoops, sine 30 degrees. That is equation number 1. And here, ma is known, all the masses are known. All right, G here, this is mb. Gravity is obviously known, d is known, 30 degrees are known. So you only have two unknowns. You have VA and you have VB like that. All right, so that goes in there. So next, what we're going to do is we are, for the additional equations, what we need to do is we need to conserve the momentum. So let us do that. So conserve, or let's call it the impulse momentum, because there is stuff happening with the impulse that may not be important, right? So impulse momentum. All right, so initially, all right, let's make this bigger. Initially, everything is at rest, right? So you go B and A. And then you have the impulse, right? Which is the weights which are going to act on it, right? So it's the weights which are causing the motion. So you can think of the weights being the impulse. But what we'll do is we'll apply a trick. We don't need to associate with that, right? So this is going to be the MAGT like that. And then you have the MBG T impulse for that mass like that, right? So you have this impulse and then you have the motion, right? So you have MA VA, and we know that's horizontal because it's on a horizontal plane. And then for the box, you will have MBVB, right? So you will have this BVB like that, right? So draw it appropriately like that. So let's say like that. So MBVB like that. All right. The issue with writing it this way is that we don't know the direction of VB. And that adds another unknown that's into the expression, right? We can enter that as into an unknown, but there is a different, quicker way to do that, right? Because the reason is, why do I need to know the direction? Because I can only use momentum conservation in the horizontal direction, right? Otherwise, I have to worry about all of these impulses, right? So you can only use the momentum conservation in horizontal. Otherwise, I have to worry about all of these vertical forces on the system, right? So in order to do that, I need to know what the direction of VB is so I can find out what its horizontal components is. But I don't know the direction. I can treat it as an unknown, and that might help out, but there is a quicker way to do it, right? So remember, this triangle over here, right? So here with the directions drawn, you can draw that simply as being equal to VBA. VBA, you do know the direction, right? It's just going to be VBA cosine 30 like that. So that's basically what we're going to do. So what we're going to say is that from this expression, this is true. Then what also means is that if you look at your coordinate frame, you can also say that VBX just looking at the scalar quantity. So all you're doing is you're compounding your I hat components now. You're looking at your I hat components now. So you have VB relative to A in the X direction like that, plus VA, whatever the X component is, right? So the VAX component we know is just equal to VA. That guy's horizontal. The VBAX component is just equal to, so if I write this out absolutely, it's just going to be my unknown that I'm treating here, VBA, right? And it's in the negative direction, so it'll be minus VBA cosine 30 degrees. So it's just the component in the horizontal direction plus VA. VA we've already set up, so this is just equal to VA I hat, right? And this is going to be VBA cosine theta I hat minus VBA, right? So that's where this expression comes from. All right, and then just with this additional unknown, I can get another expression just equating the velocities from this triangle, right? I can get that for these magnitudes, I can use the law of cosines, right? And I can say that VB squared is equal to VA squared plus VB relative to A squared minus 2VA times VBA times cosine 30 degrees, like that. Right, and that becomes, let's say, my second expression. So now I have three unknowns. I have VA, VB, and VB relative to A, right? So I need the third expression, and that comes from my horizontal momentum conservation, right? So let's do that. So selecting this guy here, moving it up, right? Initial horizontally, the moment, everything is not moving, so everything is zero, right? There is no horizontal impulse that's imparted onto the system. That's the beauty. So we don't have to add additional unknowns, right? Then that's just equal to MAVA, right? Plus MB times whatever the VB X component is. And we said that that's just equal to this expression over here. So you get this is equal to MAVA plus MB times VA minus VB relative to A cosine 30. I've just plugged in that expression on top over there, right? So this is your three expressions. So now you have three expressions for three unknowns, and you're done. So you have VA, VB, and VB relative to A, B, your expressions. All right, so let's plug this in to Mathematica. All right, so the best way to do this is that, not like that, like that. So this is the full experience you get with the recording, right? We get to see me use Mathematica, basically. I don't know if that's important to you guys. All right. Come on. This is so weird. All right. Let's say 200%. Okay. So the expressions that I'm looking for are this first one. So what I'm going to do is solve. Whoa, it's really big. 125. So solve for, all right, so let's write that expression out first. So the first one is VB squared. If you want to get fancy, you can get your writing assistant in. Right, where'd you go? It's right there. You can say, look, I want to enter it in a fancy way. Where'd you go? This way. Then you can say that is, no, what was it? It was VB, right? So VB squared like that, and that is equal to, let's use consistency. So VB like that. So that's equal to VA squared, right? So VA squared plus VB relative to A squared minus 2 times VB times VB relative to A times the cosine of 30 degrees. All right, so that is my first expression. Then, whoops. What? Why is this not moving now? Oh, come on. Why so weird? All right. Like that. So second expression, let's see, what do you want to use for second expression? Let's use our energy conservation. So you have 0 is equal to, all right, let's get fancy again. Like writing assistant, we will enter a fraction in, so we can write our 1/2 in a fancy way. Let's put it a bracket outside it to make it, what's happening? Like that. So 1/2 times MA. So MA was 25 pounds. So let's say 25 pounds for that. Remember, Mathematica doesn't know units, right? So MA, actually, no, it's not going to be 25 pounds, right? Because it's 25, another fraction coming in here. It's 25 divided by gravity, right? So where's my writing assistant? There you are. That. So that is 25 pounds divided by 32.2 foot per second squared to get the mass times, oh no, I can just use this one, right? So this one was, what was it? It was VA squared. Aha. Oop, Control C, Control V. So that's one bracket times, now we can just do good old copy pasting. So Control C, Control V. So 1/2 MB. What's the mass of B? 15 pounds. 15 there. This becomes VB. All right. Oh, it's not plus here, guys. It's not multiplication. It's plus. All right. Minus MBGD. So MB is this guy times there, times G, which is 32.2, right, foot per second squared, times D, which was 3 feet, right, if I remember correctly. Correct. Units are all consistent, times the sine of 30 degrees. All right, so that is your second equation. All right, and then finally, the last equation comes from momentum. So you have 0 is equal to MA, which is, MA was 25 pounds, right? So Control C, that guy, times VA, which is, oh, I can just write it, idiot, VA, like that, plus MB. MB is this guy here, times V, oh, so now I need another bracket. So VA, whoops, VA minus minus VB relative to A. You know what? Let's open a bracket. VB relative to A times cosine of 30 degrees. Right, so that closes that bracket, that closes that bracket, and that closes that bracket, right? And that's it, we're done. All right, and then we're solving for VA. VB, whoops, VB, VB, VB relative to A. Oh, I did not close this bracket. There you go. Oh, what did it go wrong? Oh, I didn't close this bracket. Oh, why are you so horrible? All right, give me numbers. All right, it didn't like something. What does it not like? Zero is, oh, what is this equal to weird like that? Equal to, equal to. Oh, what's going on? What's going on? It's trying to solve it. 0, comma, PA, PP. All right, this is so weird. All right, that guy there, that guy there. So it doesn't like the last expression, this guy? Oh, because I'm missing a curly bracket here. I thought I just solved that. Oh, because I put one here. There we go. All right, that worked. Awesome. All right, so we know that all the motions which we've assumed have to be positive because VBA relative to A has to move in that direction. Well, I guess the answer didn't match up. I wonder what happened there. 15. MG. Oh, that's cause. Nope, that's right. 15 times 3. I guess I could have just entered the weight here. All right, scrutiny, scrutiny. What did I mess up? Or is the book just wrong? Which is also a possibility. 4.91, 8.13.